Welcome to a lesson with Dr. Powell. Let's take a look at how we can think about triple integration, and we're going to do that with an example. So what we're going to do is we're going to calculate the volume in the x, y, z coordinate system. We're going to take in the first octant, we're going to take the crosscut of the plane x plus y plus z is equal to 1. And let's find the volume in here using a triple integral. So basically what we're going to be doing is we're going to be adding up lots of little boxes, the volume of lots of little boxes, dx, dy, dz, multiply together. That's the volume of a rectangular solid, where we have as our dimensions one direction, we have dz, maybe another one dx, another one dy. So we're going to be adding up this, and we're going to be doing it over a particular region. So we basically come up with a set of iterated integrals. Where we need to choose which variables will go where. And we do this the same way as we would for a double integral. As we go through the region, the outermost will just simply be a constant. So for instance, let's suppose our outermost is z. Z will be going, so this point right here as a z value of 1, so x value of 1, so as a y value of 1. Z will be going from 0 to 1. Now let's just pick a point on z as z is going up, because since that's the outermost. So it's kind of like a height right here at a height of z. Now what's happening here with the volume? Well, the cross section of the volume is actually a whole flat area here. So as we're going upward in z, we take a look at a cross cut of the volume. Instead of a cross cut of the area, we're looking at a cross cut of the volume. The cross cut is going to look like a triangle, just like we have here, but we can kind of look at it this way. We will. It's going to be a triangle. In fact, this triangle is going to be a right. It's going to have a right angle, because that's the x-axis, that's the y-axis. Okay, and this is supposed to be, in fact, it'll be an isosceles triangle, kind of coming up here, as we go, and mainly because we have an isosceles triangle down here, and we have a similar triangle. We've just kind of reduced the sizes of things. Okay, now we need to figure out what the area of this will be, and we're going to do that as an integral. We need to choose, are we going to be going with respect to x or with respect to y first? Okay, now let's see, if we do with respect to x would be starting at 0 at this point and be heading off to this point. Now what's that point? That point's right there. That point depends on what we choose. I mean, what our z coordinate is right there. And so we could, if we had, in fact, if we were thinking in the xy plane right here, we could do that. This line right here is actually equivalent to x plus z is equal to 1. And so we could think that x actually is equal to 1 minus z. And this is the equation of this line, relationship between x and z on this line. So if we're at this point, we want to write the x coordinate in terms of z, it would be 1 minus z. So we'd be going to 1 minus z. So x would be going from 0 to 1 minus z. Now let's pick an x coordinate on our traversal from 0 to 1 minus z. So at this particular x coordinate, we need to figure out what the range of y is going to be. So y will be going, here's the cross cut right here. Y will be, looks like it's going from 0, and it's going to this point right here. Now this point is actually on the surface, x plus y plus z is equal to 1. And so we could solve for y, and we'll figure out what that particular y value is right there in terms of x and z. So we solve for y, and we get y is equal to 1 minus x minus z. So 1 minus x minus z. Okay, so that was x and that was y. And now we have successfully come up with the triple integral that will tell us the volume of this object, which we described in space. In the next video, we'll work through the details of how to compute this as an iterated integral. Thanks for watching.